Okay, so let's take our first attempt now at using the variational method to estimate the ground state energy for helium. And so what I said at the end of the last video was that if we didn't have the interaction between the two electrons, then we could actually write down the exact wave function. And that exact wave function would be psi of R1 and R2. And that would just be equal to the product of the wave function psi100 of R1, psi100 of R2, where this is just the wave function that you would have for a single electron in a helium plus ion. So that psi100 is this one. It's just like the ground state wave function for hydrogen, except we have this factor of Z that takes into account the fact that we have charge Z in the nucleus. For helium, we have Z equals 2. Okay, so this is going to be an important wave function for us when we're applying the variational method. So the first trial wave function we're going to try for our example where you actually have the full Hamiltonian of helium with the interaction between the electrons, the first trial wave function we can try is actually just this wave function, the same wave function that would be the ground state wave function if you didn't have that interaction between the electrons. Okay, it's not a very clever choice. It's just a choice. It's a starting point. It would be the wave function if we turned off the interaction. So let's just use that. Remember, we're allowed to use any wave function in the variational method, and it's going to give us an upper bound for the energy of the helium atom. Okay, so this is going to be trial wave function number 1, and in the subsequent videos we'll improve on that, but let's just see what we get in this case. Okay, so now this wave function is already normalized because the normalization factor has been included in our definition up here. So if you were to integrate that thing, what we would want to do would be to check that if you integrate that over dr1 or d cubed r1 and d cubed r2 and take psi of r1 r2 squared, so we would want to check that that's properly normalized. In general, we might have to adjust the normalization to make sure that it is, but in this case, that integral splits up into a product of two integrals, and then each one is just the one you would calculate to check whether the psi100 wave function is normalized, and that one is because we've included the normalization factor here. Okay. So that would be step 2. And then step 3 is to compute the expectation value of our Hamiltonian, our full Hamiltonian for this state. Okay, and so for that, it's useful to know that our wave function that we've chosen, so our trial state, well, that's actually an eigenstate of H1 and of H2. So H1 on our state is minus 13.6 EV times 2 squared on our state. And that's because we've chosen that trial wave function to be the right wave function for the problem where you would just have the two separate electrons. Okay, and so for that state, the energy of the first electron would be minus 13.6 electron volts times Z squared, and the energy of the second electron would be minus 13.6 electron volts times Z squared, which is 2 squared. And then the total energy, if you didn't have interactions, would be the sum of those. Okay, but now we have interactions, and so we want to calculate the expectation value of H in our state, and so that's going to be the expectation value of H1 plus the expectation value of H2 plus the expectation value of this potential term, this VEE of R1 and R2. Okay. And so now we see why is it useful to know that our state is an eigenstate of H1 and H2. Well, it's because we can now immediately evaluate this first term. Okay, so the first term is just going to be minus 13.6 electron volts times 4. And the second term is going to be minus 13.6 electron volts times 4. Okay. But then the third term is the interesting one. And so for this one, we just have to do some integration. Okay, so this is just the standard thing. The operator that we're taking an expectation value of, it just depends on the positions of the electrons. And so if we want to take that expectation value, then what we want to do is just a big integral. So we have actually a 6-dimensional integral. So the integral over R1 and the integral over R2. And then we have our wave function squared. So psi 1, 0, 0, z equals 2 of R1 squared times psi 1, 0, 0, z equals 2 of R2 squared. And then we have our Coulomb potential, which is E squared over 4 pi epsilon naught R1 minus R2. And we just have to do that integral. So I'm not going to go through the integral here. You can see the details in Griffiths. I'll just write down the answer. And so once we take into account the value of that integral and the first two terms here, then you end up getting approximately minus 75 electron volts. Okay. So notice we don't have any parameters here. We just tried one single trial wave function. And so what we know now, based on that, is that the energy, the ground state energy of helium, is less than minus 75 electron volts. Okay. So in the next little video, we're going to improve on that and consider a class of wave functions that depends on a parameter. So that's actually going to get us much closer to the actual ground state energy of helium. You might be wondering, well, how close are we with that guess? It turns out we're just off by a few electron volts. So it's actually not so bad, but we're going to be able to get a lot closer by improving our variational ansatz.